Yep, so thank you for hanging up to this late. And in last talk, in Funk's talk, I told you that CDA is an in situ instrument, and now I'm going to tell you a dust instrument can also be used as a remote sensing instrument. And that's what we start to think about what can be done from the dust point of view instead of, except that SUDA, the surface dust analyzer on board Clipper, will fly by and collect the materials eroded from micrometeorite impact on the surface of Europa. And in addition to that, what can we do about that? And so this is basically a observation campaign concept that I'm going to present to you, and you will be the potential future reviewer or something. And there's not much science result per se, but any inputs or I think we can all work on this together. And so the keyword here is the plume. That the plume have a lot of definition, and the definition I'm define here, very narrow-minded, is the emission of materials in the gas or solid phase from the moon surface liquid reservoir and emitted into space. And in the words of Jonathan Lunin, that means free sample. So we don't really need to go deep, or there are materials available from the orbital point of view that you can collect and analyze, though certainly there's a lot of process going on from the subsurface ocean down to space. But still, that's something different from the surface material, which may be even further altered by a lot of different processes. And so this proposal observation campaign concept is that what we want to do, of course, is want to characterize water interactions in the subsurface ocean of Europa by starting the emission from the plume. And this news just really comes in time for this talk. So, and what we want to do is, that's the proposal part, is that we want to combine simultaneously Earth-based multi-wavelength observations with dust measurements from SUDA on board Europa Clipper that covering a quite significant period of time of Europa's rotation, which is about 3.5 days each orbit, and around the time when, or further before or around the time when the Clipper arrived. And what we want to know is the frequency and the timing of occurrence of the plume eruption, and of course the plume composition, which is a largely unknown. At least we can put assumptions there, but we want measurement proof. And the things is that as a stage right now, we don't know if the Clipper will really fly by the plume location, and even if it does, the plume may not be there when it flies there. So this kind of campaign is actually a way to remotely assess the plume material in the best way, in the most economic way that we can afford, without much interruption of what the mission supposed to do, and to get some extra bonus information. And so, yeah, the plume of Europa can be described as sporadic at most. Instead of this plume is rather persistent, though it has some variability, and the volcanic plume from Io is highly variable. We all know that, but this is it is a lot of unknown about Europa's plume, and that's this campaign is all about. And these are the observatory I'm have in my list, and we can see what it can do. And so here are the Earth-based observatories, space or the ground observatories, and of course SUDA on board the Clipper. And certainly it is not a limited list. You can add on whatever you can think of that is beneficial to study the plume of Europa, and I think that would be a great thing to do. And what in my mind, what I can imagine is that these optical to infrared or UV to infrared observations can help to constrain the activity of plume emissions from Europa and from Io, and I'll tell you why I care about Io later. And this has been done by HST in the far UV wavelengths. And from the ALMA array, which is sub-millimeter to millimeter, it's more like radio telescope. Now what it can do is actually to probe what molecular species are there from the plume or from the tenuous atmosphere around Europa. And this is an example showing the methanol transition, multiple transition lines from the comet. And I'm involved in one of the observations which has been done from ALMA, seeing the Europa in 2 years ago, while data is still under analysis. And from the SUDA, what we can do is that these are focusing on the images and maybe some spectra. And here is showing the neutral gas spectral composition. And for the SUDA, of course, we'll take care of the dust component, and that's the nanodust. And why is nanodust? Because we can get them from a larger distance. And we know that because we have seen that before. So the discovery of these so-called Jovian stream particles, that this is the count rate is really, really low, is in the unit of per day. That is recorded by the Ulysses spacecraft, which is a heliospheric mission that goes to Jupiter, uses gravitational assistance to go into high elliptical orbits to study solar wind at high latitudes. And there's a dust instrument on board, as this you can see here with this cover. And what it measured during the Jupiter close flyby, or around the Jupiter close flyby, around 1 year of time, that it sees these very confined bursts. You can say a burst, though it's just a few counts per day of particles hitting its dust detector. And this is later understood as these really fast and tiny particles that they are traveling with speed compared to SW doesn't stand for seawater, but solar wind, for about 400 kilometers per second, or comparable to that, very high speed, tiny particles that's beyond the calibration range of the instrument, and we can see them as a total surprise. And then the modeling start to come up with that why we can see these tiny fast particles, and thanks to the Jupiter's powerful magnetosphere, that these particles, when get charged, they basically start to be influenced by the magnetic field of Jupiter. And you can imagine that if there's a sweet spot, or another Goldilocks law for the ejection, that for particle too small, they will basically act as a plasma particle. They drive around the field line. They basically bound to the field line. And if it is too big, they basically act as a moon. They orbit, they're governed by gravity. They are bound to the Jupiter's gravitational well. And in the middle, there's a sweet spot of a few, say, tens of nanometers of particles. They can gain energy from the magnetosphere of Jupiter and get ejected. Which means another very important concept for this proposal is that it's free delivery. So you get free sample and free delivery, so it's a big discount. So it's no reason why to take it. And if you figure out the speed, basically that means the particles emitted from Jupiter system will arrive 0.35 AU in 2 days. So that's, you can expect a time delay to compare with remote sensing instrument and dust measurements, but it also means that we can actually see these from afar. We can probe any material comes out of the Jupiter system in form of nanoparticle really from far, far away. And another thing about Jovian system, I mean, all that about is good news, but the bad news is that we know most of these particles coming from Io. So the volcanic plume from Io producing these particles, and the reason we say that is because these particles are so numerous, and based on Galileo measurement, we can do a period diagram for them, and we found the Io period, for some reason, is here. And so that put a observational kind of evidence supporting that these particles are from Io. But if you have a Europa is a source, a sporadic source, actually, I think from the dynamical point of view, maybe we can separate out from the Io nanoparticle background and be able to, tell if there are activities from Europa. Okay, and this is basically a model simulation using Io as basically you can imagine the sprinkler kind of thing, that it just launching particles as it orbits Jupiter. So it's supposed to be a movie, but that's okay. and Europa will be about 9.5 Jovian radii. And for that, what particles launching from Europa will gain less energy compared to Io because it sits further outward from Io, and therefore the particles will likely be smaller and slower, but still there will certainly no problem for them to escape Jupiter, entering interplanar space to be seen from larger distance. Okay, and here I want to show you what CDA has measured during the Cassini flyby of Jupiter at the end of 2000. And so it's actually a very in terms of if you see dust as if you turn the brightness of dust, then Jupiter is certainly one of the brightest source of dust, because within the 12 hours campaign we have during the close approach, which at a distance about 137 Jupiter radii, we record about 1,000 events. So the flux is very high, and that means we will get a lot of data even at larger distance. And not just counting them, we have mass spectral capability. Even with CDA is sufficient enough to tell us what these particles are made of. And so there will be a lot of data, and so there will be even at larger distance, we should be able to have some statistics to play with and to compare with other observations. That's why we cannot do it just with dust instrument. We also need multiple wavelengths observations simultaneously to get us to provide other constraints. And some thoughts about how to form nanoparticles. So this is always an issue, because to form nanoparticles, you can either form them by fragmentation. You have a chunk of material, you smash it down to tiny, tiny particles. But of course, that takes energy. So to break into a lot of, nanoparticles has a lot of surface that take a lot of energy to create. And the other approach is a bottom-up approach. You form these particles from building up one molecule at a time. And so you form these tiny particles, which is not very difficult, as we know that there are mechanisms to do that in Earth's hydrothermal system. What we have applied this to inserters, and also just by passing through these water vapor into nozzles from the subsurface vents, you can form these tiny particles already, and Cassini plasma instrument also confirmed the existence of these particles. So it's very likely that if the plume production mechanism on Europa is similar to inserters, we will have like the vapor, water vapor, nano ice particles. And what else? So I'm thinking, if by any chance there is a process that could bring some of the materials either floating in the ocean of Europa or from the bottom of the sea through some of the convective flow to bring up to near surface, that then they could be also inject to the vents and into the plumes, and we maybe see them. So it's time to be creative, and we went to inserters with open mind, means we know nothing, but now we can really start to think about what might be there. And so to summarize what to expect, so from the dust analysis measurement point of view, we could always look at the composition and also about the dynamics. So composition-wise, we could expect water ice grains, which most likely from the condensation or nucleation in the vents. And if there could be organics, that would be also interesting. And these two kind of composition are the grains we don't expect from Io. So if we can see these type of grains as a signature of nanoparticles, then we know there we are very likely to see something from Europa. But if it's some refractory materials like silicates and sulfurous compounds, then we will need to double check with other sets of observations, and also compare with dynamics that we might be able to figure out based on their detection patterns, and also by their dynamical properties, and so on. So it's not a definite answer we can provide, but it's something that we might be able to tell if we are lucky enough. And so this is the summary of these concepts. Why we're doing this? Because the plume is variable. We don't know what exactly the condition is. And this kind of compound is low risk of operation, and it can be relatively flexible, doesn't really cost you much. And we're going to organize multi-wavelength observation plus dust measurements from larger distance. When is before, around, or during the mission. So really, really flexible. And certainly marked in yellow are some known unknowns that we don't know when exactly Clipper may arrive. We have a good idea. And so knowing where the Jupiter in the position in the sky is important for the ground-based observation. And also we don't know what facility will be available by then. Is Hubble Space Telescope will still be available. Hopefully James Webb Telescope will be there. And ALMA has its own issue because right now it doesn't really accept observation proposal for follow-up observations. They want to explore new targets. And maybe by then this restriction will be relaxed much more. And also, are there really dust production in the plume of Europa, and also the longevity of the plume? So a lot of unknowns, but still it's something I highly think that we should do. Thank you.
Time for a few questions.
Yes.
Thank you, Sean. I think that's pretty good coverage of all the possible observation, and then for the free delivery, why we don't do that. But my question is that for both optical observation, like such as JST, and then infrared and radio, as opposed to physical impacts, I think that all those different kinds of impact detection should have a different sensitivity, depending upon the size of the particles.
Certainly. I mean, I limited myself at only to see these nanoparticles because that's the particle that can be transported to larger distance, and by then we have more flexible time frame to point the spacecraft to look at Jupiter and to coordinate with other facilities. And that's why and certainly, as you point out, we are seeing different things. And that's might be a difficulty in terms of data interpretation.
Right, yeah, the SUDA is good for the nanoparticles. But I was just wondering, is that ALMA is still good for nanoparticle swarm observation?
I think I'm not an expert, but I suppose you can measure something like a continuum to measure the thermal emission. But then, I mean, the plume on Europa, because of the gravity, the plume will not be, highly extended like inserters. So it will be a tiny, small feature, maybe a few 100 kilometers on the surface. It will be difficult to resolve.
Yeah, okay.
Yeah.
Sorry, quick question. You had a slide where you actually showed data from the Cassini encounter. I'm surprised that the Sulphur Peak, if I can see that correctly, is so small. Are we looking at?
Oh, yes. So this is Funk's result in 2006, and the conclusion is basically these particles, or these nanoparticles from EO, is composed of, the main constituent is sodium and chloride. And the reason why is that not sulfur, because sulfur has relatively low, or the interpretation is that sulfur has relatively low condensation temperature, and so from the for the particles to get to the high latitudes from the plume of a volcanic plume, it needs to be more likely for the first condensate have high melting point. Material has high melting point that already in the form of a solid at high latitude to acquire electric charge from the ionosphere, and then it could take off from the gravity of EO and become, the acceleration. And that's why it's kind of a selection process that we preferably see some materials from that.